Picture yourself floating in the deepest reaches of outer space, millions of light years from the nearest star. No planets, no gas clouds, no cosmic dust. Nothing but pure, absolute emptiness stretching endlessly in every direction. You'd think this would be the ultimate definition of nothingness, right? A perfect void where literally nothing exists. At these quantum scales, something called the uncertainty principle kicks in. This isn't just a limitation of our measuring tools, it's a fundamental law of nature that says certain properties of particles can never be precisely determined simultaneously. And this has a shocking consequence. It means that even in the most perfect vacuum you can create, even in the most empty space possible, there's still energy present. There has to be. This energy is called zero-point energy, and it exists even at absolute zero temperature, the coldest temperature theoretically possible, where all thermal motion stops completely. Even when everything is as still and cold as it can possibly be, this energy is still there, quietly humming away in the background of empty space. Now you might be thinking, okay, so there's some energy in empty space, so what? But here's where it gets absolutely wild. This isn't just a little bit of energy we're talking about. According to our best calculations, the amount of energy contained in the quantum vacuum is so enormous that it should be ripping apart the fabric of reality itself. Let me put this in perspective. Take a volume of space the size of a coffee cup. According to quantum field theory, the zero-point energy contained in that tiny volume should be enough to boil away all the oceans on Earth. In fact, it should be enough to boil away every ocean on every planet in the observable universe, with energy left over to spare. But clearly, your morning coffee isn't spontaneously exploding from the vacuum energy around it. This creates what physicists call the vacuum catastrophe, a mind-boggling discrepancy between what the math predicts and what we actually observe. The theoretical prediction is off from reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. To put that in context, this is possibly the largest discrepancy between theory and observation in the entire history of science. So what's going on here? Are physicists just completely wrong about quantum mechanics? Well, not exactly. See, while we can't directly tap into all that vacuum energy, thank goodness, or we'd all be vaporized, we can definitely detect the effects of quantum vacuum fluctuations. And these effects are not only real, they're measurable, reproducible, and absolutely essential to how our universe works. The quantum vacuum is constantly alive with what physicists call virtual particles. These aren't particles in the traditional sense. You can't catch them or isolate them or put them in a jar. Instead, they're temporary fluctuations in the quantum fields that fill all of space. These virtual particles pop into existence, impairs a particle and its antimatter twin, borrow energy from the vacuum for an incredibly brief moment, and then annihilate each other and disappear. Now, I know what you're thinking. Virtual particles that pop in and out of existence? That sounds like complete nonsense. And honestly, if I hadn't seen the experimental evidence myself, I'd probably think the same thing. But here's the beautiful thing about science reality. It doesn't care what sounds reasonable to us. It just is what it island. These virtual particles are constantly flickering in and out of existence everywhere around you. Right now, as you're listening to this, trillions upon trillions of particle pairs are spontaneously appearing and vanishing in the space between your atoms, in the air around you, in the empty space between the Earth and the Moon. It's like reality itself is constantly bubbling with invisible activity. And here's the kicker. These virtual particles aren't just theoretical curiosities. They're responsible for some of the most important forces in nature. Virtual photons carry the electromagnetic force that holds your atoms together. Virtual gluons mediate the strong nuclear force that keeps atomic nuclei from flying apart. These invisible, temporary, unreal particles are literally what keeps reality glued together. Well, what if I told you that this seemingly empty space is actually one of the most energetic, chaotic, and downright bizarre places in the entire universe? What if I told you that this nothingness is so jam-packed with invisible activity that it makes Times Square on New Year's Eve look like a quiet library. And what if I told you that modern physics has proven beyond any doubt that truly empty space doesn't just not exist, it literally cannot exist? But wait, it gets even more mind-bending. In 1948, a Dutch physicist named Hendrik Casimir made a prediction that seemed almost too bizarre to believe. He calculated that if you took two perfectly flat, perfectly conducting metal plates and placed them incredibly close together in a vacuum, the quantum vacuum itself would push them together with immeasurable force. Think about that for a second. Empty space, pure nothingness, creating a physical force that can move real objects. It sounds like magic, doesn't it? The physics behind this is absolutely beautiful. Between those closely spaced plates, only certain wavelengths of virtual photons can exist specifically, those that fit neatly between the plates like standing waves on a guitar string. But outside the plates, virtual photons of all wavelengths continue to exist normally. This creates an imbalance, a difference in the quantum vacuum pressure on either side of the plates. And that pressure difference creates a real, measurable force that pushes the plates together. For decades, this remained just a theoretical prediction, but in 1996, physicist Stephen Lamoureux finally measured it. Using incredibly precise equipment, he demonstrated that two plates, separated by less than a micrometer, about 1/100th the width of a human hair, were indeed being pushed together by the quantum vacuum with a force of less than a billionth of a Newton. The measurement matched Casimir's 50-year-old prediction to within 5%. This was proof positive that empty space isn't empty at all. Since that groundbreaking experiment, scientists have discovered that the Casimir effect is far more versatile than anyone initially imagined. It turns out you can actually flip the force from attractive to repulsive depending on what materials you use and how you arrange them. In 2008, researchers managed to create a repulsive Casimir effect by placing a gold-coated sphere and a silica plate in a special liquid called bromobenzene. Instead of pulling together, the quantum vacuum actually pushed them apart. This might sound like a neat physics parlor trick, but it's actually opening up incredible possibilities for nanotechnology. Imagine building microscopic machines where the moving parts never actually touch each other because they're held apart by the quantum vacuum itself. No friction, no wear, no mechanical breakdown. Just the invisible energy of empty space doing all the work. But the Casimir effect is just the tip of the iceberg when it comes to the bizarre world of vacuum physics. Scientists are now discovering that they can actually use the quantum vacuum to control the properties of materials in ways that seem almost supernatural. Welcome to the mind-bending world of the quantum vacuum, where everything you thought you knew about emptiness gets turned completely upside down. I'm about to take you on a journey into one of physics' most shocking discoveries, one that reveals the universe is far stranger, far more alive, and far more beautiful than we ever dared imagine. Here's what's happening. Researchers have figured out how to tune the interaction between vacuum field fluctuations and electrons confined to move in just 2 dimensions. By adjusting this interaction, they can literally change how the material behaves at a fundamental level. It's like having a universal remote control for matter itself, and the remote is powered by empty space. This breakthrough could revolutionize everything from quantum computing to electronics. The team working on this has even suggested they might be able to create exotic particles called anyons particles that exist only in 2-dimensional systems and have no equivalent in our normal 3-dimensional world. These anyons could be the key to building quantum computers that are more stable and powerful than anything we can create today. But perhaps the most mind-blowing aspect of all this is what's happening right now in laboratories around the world. Scientists are preparing to do something that sounds completely impossible. They're getting ready to create light from pure darkness. Let me explain what the ones that pop in and out of existence everywhere means. Remember those virtual particles I mentioned, the quantum vacuum? Well, it turns out that if you hit them with powerful enough laser beams, you can actually knock some of them into becoming real particles. Real photons of light, created literally from nothing but empty space and intense electromagnetic fields. The process is called vacuum 4-wave mixing, and it works like this. You take 3 incredibly powerful laser beams and focus them at exactly the same point in empty space. The combined electromagnetic field is so intense that it actually jolts the virtual particles in the quantum vacuum, causing them to scatter real photons in a fourth beam of light. It's like playing billiards with invisible balls that don't technically exist, and somehow getting real balls to roll out of the collision. This isn't just theoretical anymore. Oxford scientists have already run computer simulations that show exactly how this process works, and they've confirmed that the physics checks out perfectly. The simulations show light literally emerging from darkness photons being born from the quantum vacuum itself. And here's the incredible part. We're just about to have the technology powerful enough to actually do this in real life. Facilities like the UK's Vulcan 2020 laser system, Europe's Extreme Light Infrastructure project, and China's Station for Extreme Light are all coming online right now, with power levels that could make this fantasy become reality. These aren't your everyday laser pointers we're talking about. These are machines that can generate electromagnetic fields so intense they can actually grab hold of the quantum vacuum and shake real particles loose from it. We're talking about power levels that can literally bend the fabric of empty space. But wait, there's more. Scientists in Germany are planning what might be the most ambitious quantum vacuum experiment ever attempted. They want to directly observe the quantum fluctuations in completely empty space, no matter. No particles, no interference of any kind. Just pure vacuum, and the most sensitive detection equipment ever built. The challenge is absolutely staggering. They're trying to detect changes in the polarization of X-ray photons that occur when they interact with virtual particles in the quantum vacuum. The expected signal is so weak that only about 1 in a trillion X-ray photons will show the effect they're looking for. It's like trying to hear a whisper in the wearing earplugs. Now, before we dive headfirst into this rabbit hole of quantum weirdness, I need to warn you this stuff is going to challenge some of your most basic assumptions about reality. We're talking about invisible particles popping into existence out of pure nothingness, energy being borrowed from empty space itself, and forces that can literally be created from the absence of everything. If that sounds impossible, well, that's exactly what physicists thought too, until they started measuring it. If middle of a thunderstorm while this experiment succeeds, it will be the first time in history that humans have directly observed the quantum vacuum without any matter present to help with the measurement. We'll finally be looking at pure nothingness and watching it buzz with invisible activity. But here's what makes this even more exciting. Success could either confirm our current understanding of quantum physics, or it could reveal completely new laws of nature. The experiment is so sensitive that it might detect previously unknown particles, things like axions, hypothetical ultralight particles that could help explain some of the biggest mysteries in cosmology. Think about that for a moment. Empty space might be hiding entirely new types of matter that we've never discovered before. The vacuum itself could be a treasure trove of exotic physics waiting to be uncovered. This brings us to one of the most profound puzzles in all of modern science, the vacuum catastrophe I mentioned earlier. Remember how I said the theoretical energy in empty space should be enough to boil all the oceans on Earth? Well, this creates a massive problem when we try to understand the universe on the largest possible scales. You see, according to Einstein's general relativity, energy is equivalent to mass, and mass creates gravity. If the quantum vacuum really contained all that energy we calculate it should have, its gravitational effect would be absolutely catastrophic. The universe would either have collapsed immediately after the Big Bang, or it would have expanded so rapidly that no stars, galaxies, or planets could ever have formed. But obviously, here we are. Stars exist, galaxies exist, you exist. So somehow, either our calculations about vacuum energy are completely wrong, or there's some mysterious mechanism that cancels out almost all of its gravitational effects. This is what physicists call the cosmological constant problem, and it represents possibly the largest gap between theory and observation in the history of science. The vacuum energy we calculate should be 10 to the power of 120 times larger than what we actually observe affecting the expansion of the universe. To put this number in perspective, Imagine you predicted that a person would weigh 10 to the power of 120 pounds, but when you put them on a scale, they weighed 150 pounds. Your prediction wouldn't just be wrong, it would be so spectacularly, impossibly wrong that you'd have to question whether you understood anything about physics at all. And yet, this is exactly where we find ourselves with the quantum vacuum. Our most successful theories in physics, quantum mechanics, and general relativity, when combined together, produce predictions about empty space that are more wrong than anything has ever been wrong in the history of human knowledge. Some physicists think the solution might involve supersymmetry, a theoretical extension of the standard model that predicts every particle has a superpartner with different properties. Others believe we might need extra dimensions beyond the three of space and one of time that we experience directly. Still others think the problem points to a fundamental flaw in how we understand either quantum mechanics or gravity. And here's the kicker, we're not just talking about abstract theoretical physics that exists only in dusty textbooks. This invisible energy of empty space affects everything from the smallest atoms to the largest structures in the cosmos. It's influencing the expansion of the entire universe. It's responsible for forces you experience every day, and scientists are now figuring out how to harness it to build technologies that sound like pure science fiction. But here's the thing that keeps physicists up at night. Despite this enormous theoretical problem, the effects of the quantum vacuum that we can measure are absolutely, perfectly real. The quantum vacuum isn't just some abstract concept that exists only in the minds of theoretical physicists. It's actively shaping the world around you in ways that would sound like pure science fiction if we didn't have the experimental evidence to prove it. Take the atoms in your body right now. Every single electron orbiting every single nucleus is constantly interacting with virtual particles from the quantum vacuum. These interactions are so fundamental that they actually shift the energy levels of electrons in measurable ways. This is called the Lamb shift, and it's been verified to incredible precision in laboratories around the world. What this means is that the quantum vacuum is literally helping to determine the properties of every atom in existence. The exact frequencies of light that atoms can absorb and emit, the chemical bonds that hold molecules together, even the stability of the matter that makes up your body. All of it is influenced by the invisible flickering of virtual particles in empty space. But it goes even deeper than that. The quantum vacuum plays a crucial role in one of the most mind-bending phenomena in all of physics: black hole evaporation. Yes, you heard that right. Black holes, those cosmic monsters that devour everything, including light itself, are actually slowly dissolving away thanks to the quantum vacuum. Here's how it works, and it's absolutely beautiful in its strangeness. Near the event horizon of a black hole, that point of no return where not even light can escape, virtual particle pairs are constantly popping into existence just like everywhere else in the universe. But here's the twist. Sometimes one particle from the pair falls into the black hole while the other escapes. When this happens, the escaping particle becomes real, carrying away a tiny bit of the black hole's energy. Meanwhile, the particle that fell in has negative energy relative to the outside universe, which actually decreases the black hole's mass. Over enormous periods of time, this process causes black holes to slowly evaporate completely. This phenomenon, called Hawking radiation, means that the quantum vacuum is essentially eating black holes from the inside out. The largest black holes in the universe will take longer than 10 to the power of 60 years to evaporate completely. That's a trillion times longer than the current age of the universe. But smaller black holes evaporate much faster, and if they get small enough, they'll explode in a burst of energy that would make nuclear weapons look like firecrackers. Think about the implications of this for a moment. The same quantum vacuum that's buzzing away invisibly in your living room is powerful enough to completely destroy the most extreme objects in the cosmos. Empty space isn't just energetic, it's literally capable of dismantling black holes. So buckle up, because we're about to explore why the most empty place you can imagine is actually the most full, why nothingness might be the most important something in existence, and how this discovery is revolutionizing our understanding of reality itself. Now, This brings us to perhaps the most tantalizing question of all. Can we actually harness this incredible energy? Can we tap into the quantum vacuum to power our civilization? This is where things get both exciting and frustrating. In principle, the quantum vacuum contains essentially unlimited energy, but accessing that energy is a completely different story. It's a bit like being surrounded by an infinite ocean but not having a bucket to collect the water. The fundamental problem is thermodynamics. To extract useful energy from any system, you need to create a difference, a hot reservoir and a cold reservoir, or a high-pressure region and a low-pressure region. But the quantum vacuum is everywhere, all the time, at exactly the same energy density. It's like trying to generate electricity from a completely uniform magnetic field. There's energy there, but no gradient to exploit. However, and this is where it gets really interesting, recent theoretical work suggests there might be ways around this problem. Scientists have discovered that under certain exotic conditions, it's actually possible to borrow energy from the quantum vacuum as long as you pay it back with interest later. This concept is governed by something called the quantum null energy condition, which sets strict limits on how much energy you can borrow and for how long. The amount you can borrow depends on a quantum property called entanglement entropy, essentially a measure of how quantum mechanical a system island. Near the edge of a black hole, where space-time is severely warped and quantum effects become extreme, it might actually be possible to create regions of negative energy density by borrowing from the vacuum. This borrowed energy could theoretically be used to create exotic phenomena like traversable wormholes or faster-than-light communication. But before you start planning your vacation to Alpha Centauri, let me bring you back down to Earth. These effects require conditions so extreme that they exist nowhere in our solar system, and possibly nowhere in the observable universe except near black holes. We're talking about energy densities and space-time curvatures that are so intense they would instantly destroy any known form of matter. Still, the fact that such possibilities exist even in principle is absolutely remarkable. It suggests that the quantum vacuum might hold keys to technologies we can barely imagine. And speaking of barely imaginable technologies, scientists are already starting to explore more practical applications of vacuum effects. The Casimir force I mentioned earlier is being investigated for use in microelectromechanical systems, tiny machines built on computer chips that could benefit from friction-free operation. Imagine microscopic gears and levers that never wear out, because their moving parts are held apart by quantum vacuum forces. Or sensors so sensitive they can detect individual molecules by measuring how they disturb the vacuum fluctuations around them. These aren't distant dreams. Researchers are working on prototypes right now. Let's start with a simple question that's been puzzling humans for thousands of years. What is empty space, really? For most of human history, this seemed pretty straightforward. Empty space was just empty. It was the absence of stuff. The ancient Greeks called it the void, a complete nothingness that existed between atoms. Even Isaac Newton, arguably one of the greatest scientific minds in history, thought of space as an absolute, unchanging stage where matter could move around. There's even more exotic research happening in laboratories around the world. Scientists are exploring whether vacuum fluctuations could be used to create new types of materials with properties that don't exist in nature. By carefully controlling how electrons interact with virtual particles, they might be able to design materials that are perfect conductors at room temperature, or substances that bend light in impossible ways. The potential applications seem limited only by our imagination. Quantum vacuum effects could lead to new types of sensors that can detect gravitational waves or dark matter. They might enable quantum computers that are naturally protected from environmental interference. They could even help us develop new forms of propulsion for spacecraft that don't require carrying fuel. But perhaps the most profound implication of the quantum vacuum goes beyond any practical application. It fundamentally changes how we think about the nature of reality itself. For thousands of years, humans have thought of nothingness as the absence of everything, a blank void where nothing happens and nothing exists. The quantum vacuum reveals that this intuition is completely wrong. Nothingness is actually the most active, energetic, creative force in the universe. It's constantly generating particles, mediating forces, and shaping the behavior of everything that exists. In a very real sense, the quantum vacuum is the closest thing physics has discovered to what ancient philosophers and mystics called the source of all being. It's the creative principle from which all matter and energy emerge, the invisible foundation upon which all of reality rests. This has profound implications for how we understand causation, existence, and the fundamental nature of space and time. If empty space is full of invisible activity, if nothingness is actually the most fundamental something, then our basic categories for understanding the world need to be completely reconsidered. Some physicists have suggested that what we think of as solid matter is really just a temporary organization of vacuum fluctuations, patterns of emptiness, that have somehow stabilized into the illusion of substance. From this perspective, you aren't made of atoms moving through empty space. You are empty space that has learned to think it's made of atoms. The quantum vacuum also raises deep questions about the nature of information and consciousness. If virtual particles are constantly carrying information about quantum states throughout empty space, does this mean the vacuum itself has a kind of memory? Could the universe be processing information at the most fundamental level through quantum fluctuations that exist everywhere at once? These aren't just philosophical speculations. They're questions that could have testable consequences as our technology becomes more sophisticated. If consciousness is somehow related to quantum information processing, then understanding the quantum vacuum might be the key to understanding minds, awareness, and the hard problem of consciousness itself. We're standing at the threshold of a new era in physics, where empty space is revealing secrets that challenge our deepest assumptions about reality. The quantum vacuum isn't just empty space with some interesting properties, it's a fundamental feature of existence that connects quantum mechanics to cosmology, particle physics to consciousness, and the smallest scales of reality to the largest. This classical view dominated physics for centuries, and honestly, it makes perfect sense from our everyday experience. When you look at the space between your fingers right now, it sure seems empty, right? There's nothing visible there, nothing you can touch or feel, it's just nothing. And we're just getting started. The experiments I mentioned earlier, creating light from darkness, directly observing vacuum fluctuations, using empty space to control matter, these are only the beginning. As our technology advances, we'll develop even more powerful ways to probe and manipulate the quantum vacuum. Future experiments might reveal entirely new particles hiding in the vacuum's invisible dance. We might discover that empty space contains multiple layers of reality, each with their own virtual particles and forces we haven't even imagined yet. Some theoretical physicists are already speculating about vacuum domains, regions where the quantum vacuum behaves differently, creating pockets of exotic physics scattered throughout the universe. But here's where things get really wild. Scientists are starting to realize that the quantum vacuum might not be the same everywhere. Just like water can exist as ice, liquid, or steam depending on temperature and pressure, the quantum vacuum might exist in different phases depending on the conditions around it. Near extremely massive objects like neutron stars, or in regions with intense magnetic fields, the vacuum itself might undergo phase transitions. These cosmic laboratories could be brewing versions of empty space that follow completely different rules than the vacuum we're familiar with here on Earth. Imagine regions of the universe where virtual particles behave differently, where the Casimir effect works in reverse, where the fundamental constants of nature have slightly different values because the vacuum itself is in an exotic state. These aren't just theoretical possibilities. Astronomers are actively searching for evidence of vacuum phase transitions in the cosmos right now. Some of the most energetic phenomena we observe, gamma ray bursts, fast radio bursts, the behavior of matter falling into black holes might actually be signatures of the quantum vacuum, undergoing dramatic changes in extreme environments. We might be witnessing empty space itself transforming from one state to another on scales that dwarf entire solar systems. This connects to one of the most ambitious ideas in modern cosmology, eternal inflation. According to this theory, our entire observable universe might be just one bubble in an infinite cosmic foam, where each bubble represents a different phase of the quantum vacuum. In some bubbles, The virtual particles might be completely different. In others, the forces of nature might work in ways we can't even comprehend. If this is true, then the quantum vacuum isn't just the foundation of our reality, it's the foundation of countless realities, each with their own physics, their own particles, their own possibilities. The emptiness between the stars suddenly becomes a gateway to infinite worlds of possibility. But let's bring this back to something you can actually experience. Right now, as you're listening to this, the quantum vacuum is actively participating in every biological process in your body. The chemical reactions that power your neurons, the quantum tunneling effects that help enzymes work, even the quantum coherence that might play a role in photosynthesis in plants, all of these depend on the invisible activity of empty space. Some researchers are investigating whether quantum vacuum effects might play a role in biological systems that seem almost impossibly efficient. How do birds navigate using Earth's magnetic field? How do some enzymes catalyze reactions faster than should be theoretically possible? How do certain biological processes maintain quantum coherence at warm temperatures where it should instantly disappear? But here's where things start to get interesting. In the early 1900 seconds, as physicists began developing quantum mechanics, they stumbled upon something absolutely revolutionary. They discovered that at the tiniest scales of reality, scales smaller than atoms, smaller than anything you can possibly imagine, the rules of the game change completely. The answer might be that life itself has learned to exploit the quantum vacuum. Evolution might have discovered ways to harness virtual particles and vacuum fluctuations to create biological quantum computers that operate inside living cells. Your body might literally be using the energy of empty space to power some of its most essential functions. This opens up incredible possibilities for biotechnology and medicine. If we can understand how biological systems interact with the quantum vacuum, we might be able to design new drugs that work by manipulating vacuum effects, or develop medical treatments that harness the healing power of empty space itself. But perhaps the most mind-bending possibility is that consciousness itself might be intimately connected to quantum vacuum fluctuations. Some theoretical physicists have proposed that awareness, subjective experience, and the hard problem of consciousness might emerge from the way information propagates through virtual particle networks in the quantum vacuum. Think about it this way. Your brain contains roughly 86 billion neurons, but the quantum vacuum contains an essentially infinite number of virtual particles fluctuating in complex patterns. What if consciousness isn't generated by neurons firing, but by the way your brain's electromagnetic fields interact with and organize the virtual particle fluctuations in the space between your neurons? This would mean that your thoughts, your experiences, your sense of self aren't just happening inside your skull. They're patterns of organization in the quantum vacuum that extends throughout your entire body and beyond. Consciousness wouldn't be produced by matter. It would be a way that empty space organizes itself into awareness. So there you have it, the quantum vacuum, the strangest, most energetic nothingness in existence. We've journeyed from virtual particles dancing in empty space to black holes slowly evaporating away, from the Casimir effect pushing metal plates together to scientists preparing to literally create light from pure darkness. We've seen how the void between your atoms is more active than the busiest city street, and how the emptiness that surrounds us might hold the keys to consciousness itself. The next time you look up at the night sky and see that vast emptiness between the stars, remember you're not looking at nothing. You're looking at the most fundamental creative force in the universe, buzzing with invisible activity, mediating every force, shaping every atom, and perhaps even giving rise to the very thoughts you're thinking right now. Empty space isn't empty. It's everything.